scientific research is an outgrowth of our insatiable human curiosity. We all have questions about our natural world, and as we saw in the last lecture, science is often the very best way to discover how to answer questions about how the physical universe works. This process of discovery employs what's called the scientific method, which can be idealized as a cyclic process of inquiry based on observations, synthesis, hypothesis, and then predictions that lead to more observations. You know, too often science educators focus on the most firmly established of scientific answers. They require students to memorize lengthy lists of facts, vocabulary, and I think in the process, the dynamic, creative process of scientific inquiry is sometimes shortchanged. In the last lecture, I told you about the National Science Education Standards. These call for science education reform centered on the idea of science as a process of questioning. The content of science is thus placed in a much broader human context. Science's approach is a process driven by curiosity. This lecture, which is the second in our series, is thus about the nature of scientific questions. You know, it's sort of a philosophical approach, but I think this is a really exciting part of science, understanding these questions and how they behave. So I have two objectives. First, I want to consider the surprising nature of scientific questions themselves. And then I'm going to tell you about the scientific method by which scientists attempt to answer questions about the natural world. So, what makes scientific questions different from other kinds of questions? If you examine different ways of knowing, it soon becomes obvious that questions in science versus philosophy versus the arts versus religion and so forth differ in their character and in their approach to the resolution. So to begin with, I want to tell you about 6 distinctive aspects of scientific questions. First, many important questions are completely beyond the realm of science. You have to recognize this fact as a scientist. You know, science can't tell you the meaning of life. It can't tell you who you should marry, or whether to have children, or if God exists. Science addresses only those questions that can be answered by reproducible observations, by controlled experiments, and these guided by theory of mathematical nature. Economist and philosopher Kenneth Boulding, he said something really funny. He said that science is the art of substituting unimportant questions that can be answered for important questions that cannot. Let me repeat that quote. Science is the art of substituting unimportant questions that can be answered for important questions that cannot. Nevertheless, science informs many of the most important non-scientific questions in our lives, including choices about health and work and relationships. Should you have children? Science can't answer the question, but your decision might be influenced by a family history of genetic disease. What is the meaning of life? Does God exist? And again, science can't answer the question, but I would argue that you can't answer those questions without some degree of understanding of the nature of the physical universe in which we exist. Of course, there are also many questions that are scientific, and that leads to my second point about scientific questions. A second aspect of scientific questions is that they are richly varied in scope and content. Scientific inquiry is as diverse as the natural world is itself. But it turns out that most scientific questions can be divided into one of 4 broad categories, and I call them existence questions, origin questions, process questions, and applied questions. First always comes existence questions. They ask what objects and phenomena occur in the natural world. You know, the scientific explorers for centuries have reveled in voyaging to exotic lands. They pursue animal, plants, mineral specimens. And perhaps the most famous of these scientific explorers was Charles Darwin, who cut his eye teeth as naturalist aboard the HMS Beagle. In fact, Darwin formulated the basic framework for his theory of evolution on that scientific expedition. As a result of expeditions like this, we have just a wealth of reference books, bird books that show all the different kinds of birds that exist in a particular area. I'm sure you've seen this kind of bird. Maybe you have one yourself and you use this kind of book yourself. They're mineral books that list all the different known species of minerals, page after page of them. These reference books are the result of centuries of work. There are even atlases. I have here an atlas of galaxies. It's an entire book that has nothing but photographs of different kinds of galaxies. Again, this is describing what's out there, what exists. Chemists have isolated element after element. They developed a periodic table of the elements as a result. Physicians, they dissect a diseased corpse and examined all the different kinds of diseases. Astronomers catalog countless stars. Physicists catalog different kinds of physical phenomena. And this is ongoing today. Various scientists look for new galaxies and catalog them, or they sequence genomes, they isolate viruses, find new planets. You probably read about finding new dinosaurs. We're constantly searching for what's out there. Then there's the second kind of scientific question, called origin questions, which explore how natural objects and phenomena came to be. These are neat questions. It's the thing that I'm most excited about in science. Questions about the origin of the universe, origin of Earth, the origin of life itself are really among the most fascinating mysteries of science, and they have to be answered with a plausible sequence of events. They have to be deduced from contemporary evidence, constrained by natural law. So origin questions, to answer them, involves telling a story, a historical story. And that's quite different from tabulating lists of birds or stars. And then the third kind of scientific question. These are called process questions, and they ask how nature works. These questions, which are very closely linked to inquiries about origins, explore how stars evolve, how rocks erode. You can think about how cancer develops, how atoms interact in chemistry, how fungi reproduce. They're all different kinds of questions about process. Descriptions of this dynamic interplay in the evolution of natural systems helps us to understand the past and the present, and in part to predict the future of our physical surroundings. And then finally, the fourth kind of a question, what I call applied questions. These look for ways to manipulate the physical world to our advantage. And that can be curing disease, it can be devising new materials for our benefit, modifying the environment. There's so many ways that scientists use their knowledge in these applied sorts of ways. Such questions are often very specific, and they're rooted in technology. So scientists search for ways to make safer cars, produce cleaner energy, cheaper food, make us live longer, all these different ways that scientists can help our lives. Most newspaper stories that relate to science in one way or another focus on some aspect of applied questions. Of course, these practical pursuits have to be tied to the other type of scientific questions. You can't manipulate nature without first understanding how it works. If you're going to cure infectious diseases, you need to have a knowledge of what the infectious organisms are and how and why they behave the way they do. If you're going to build a skyscraper, you need to have a detailed knowledge of the properties of materials. So in this way, all types of scientific questions are closely intertwined, they're interconnected. A third aspect of scientific questions, that's that old answers to old questions often lead to new questions. Let me give you a quote. In 1843, the art critic John Ruskin, he lamented that to know anything well involves a profound sense of ignorance. Well, this sentiment strikes a very responsive chord with scientists today. We just can't escape the fact that the more our knowledge about any scientific subject grows, the more we realize how much we don't know. This situation is especially true for unexpected findings. There's so many unanticipated discoveries that open up vast new areas of research. The discovery of X-rays, for example, it led to advances in medical technology and opened these huge fields, X-ray crystallography and X-ray astronomy. The discovery of plate tectonics not only transformed earth sciences, but it changed climate studies, it changed anthropology, it changed the thought about evolutionary biology as well. Similarly, advances in understanding the genetic code and quantum mechanics and radioactivity, all of which we'll learn about in this series of lectures, all those opened up whole new areas of research. The answers to existence questions invariably lead to questions about process and origins. Imagine, for example, what would it mean to discover extraterrestrial life? That's such a cool idea. That one discovery would open up vast new research areas in biology, in technology, in all sorts of areas that we can't imagine now. You may have heard the silly statement that we are nearing the end of science. Well, I'd argue exactly on the contrary, that science is an endless frontier. My fourth point is that scientific questions are often interconnected in very surprising ways. As scientists explore the most sweeping unanswered questions, they often discover links between what at first seem to be completely unrelated topics. The big questions tend to blur all the traditional boundaries of science, and they unify the study of our world. For example, we're going to see that discoveries by Earth scientists of new models for our planet's dynamic interior bear directly on the understanding of such diverse subjects as climate change and ore deposits and life's origin and evolution. We're going to see that studies of ancient mass extinctions in the fossil record, which might seem like a very arcane subject, they're providing models for understanding the importance of today's global environment. Scientific questions can also be linked by a philosophical approach. One of those approaches is called reductionism. It's based on the assumption that complex systems can be understood by examining the behavior of various fundamental building blocks. Let me give you some examples. Particle physicists search for a theory of everything, and that's the idea that everything can be explained by studying interactions of subatomic particles. By the same token, there's some molecular biologists who adopt the principle that all biology follows from genetic traits. So they look at genes as the fundamental unit. And then at the opposite extreme, some scientists are now thinking about extremely complex systems in sort of a holistic way. Ecosystems, or the brain, or even the universe as a whole can be examined as collective systems that display what are known as emergent properties. That is, properties completely unlike those of smaller components. Let me give you some examples. Atoms. They interact to form an astonishing variety of molecules that don't behave like individual atoms. And then molecules can combine to form living cells that don't behave like individual molecules. And then you can have lots of cells get together, and individual cells can produce consciousness and thought, which are properties that no single cell could display. So some big questions related to life and environment thus focus on the often surprising ways that complex systems evolve. A fifth aspect of scientific questions. Some questions are not now scientific, but they may be someday. This is kind of a surprising conclusion, but imagine in 1900, before Edwin Hubble discovered galaxies, questions about the origin of the universe were just not in the realm of science. There was no observation you could make that could shed light on how the universe began. But the situation changed when they constructed big new telescopes. Today, I think that the study of consciousness is probably beyond science too. We don't even have a good operational definition of what consciousness is. But that situation may very well change as we discover more about the physical workings of the brain, and maybe 100 years from now, consciousness will be a firmly established scientific subject. And now my sixth and my last point about scientific questions. It's just scientific questions can't be answered completely. Now, this may seem surprising that you can't answer questions about the natural world completely, but let me give you some reasons why this is true. Turns out there are at least 4 factors that prevent us from obtaining complete answers to many scientific questions. And the first factor is that old nemesis, experimental error. All measurements, no matter how accurate you make them, contain some error. Think about making a measurement called thermal expansion on a metal bar. When you heat up a piece of metal, it expands. And to document this effect, you need to measure 2 things. You need to measure the length of the bar, and you need to measure the temperature of the bar. And you can do both those measurements with exquisite precision and accuracy. They're state-of-the-art thermometers that can pinpoint temperatures to 1,000th of a degree. And you can use something called laser interferometry to measure the length of the bar to 1,000,000th of an inch. And yet there's always going to be some error. There's always room for improvement. Science is a never-ending pursuit, in part because we're constantly devising new techniques for making improved observations and measurements. So you're going to see lots of articles about bigger telescopes and faster electronics, more sensitive analytical methods. All these regularly improve the available accuracy and precision, and they inspire new questions and new experiments on old questions. A second reason why scientific questions can't be answered completely lies in what's called the uncertainty principle. That was first proposed by the German physicist Werner Heisenberg, and for that reason it's sometimes called the Heisenberg uncertainty principle. It turns out that at the subatomic scale, that's the scale of the atom and the electron, every measurement alters the object being measured. That's one of the most unsettling discoveries in quantum mechanics. At nature's smallest scale, matter and energy comes in discrete packets called quanta. Energy or mass comes in units. And any observation of a quantized object, for example, if you want to measure the velocity of an electron, that causes the particle to move, to change. And the measurement itself changes the thing you're measuring. Thus, every observation of a natural phenomenon has a built-in uncertainty at that atomic scale. And there's a third source of uncertainty. It's called chaotic behavior. Many natural systems, it turns out, are inherently unpredictable, even with the best of mathematical models. Scientists like myself believe in an orderly universe. We believe in cause and effect, in which any given set of initial conditions leads to a predictable outcome. But these recently discovered chaotic systems, that includes things like dripping faucets, human heartbeats, even the weather. It turns out that the most minuscule variation in the initial conditions of those systems can radically alter their behavior months and weeks down the road. Since every measurement of initial conditions contains some error, that means the future behavior of chaotic systems cannot be predicted accurately. And then there's a fourth reason why we can't know everything, and that's the finite speed of light. Indeed, there are daunting limitations placed on us by space and time. Given the incredible size of the universe, it's billions of light years across, the cosmic speed limit of a paltry 186,000 miles per second prevents us from knowing the state of even the closest neighboring stars at this moment. And other galaxies, which are much more distant, are forever beyond our reach. Not only that, but the forward direction of time prevents us from ever visiting the past. So unless scientists discover some dramatic new and unexpected ways to manipulate space and time, we're always going to be confined to the tiniest part of the universe. Well, all those reasons might together sound kind of pessimistic, but science still has discovered amazing structure to the universe. It's discovered natural laws. And so in spite of these and other inherent limitations on inquiry, the methods of science provide the most powerful tool we have to understand and modify our physical world. And the systematic process by which scientists discover principles of the natural world, that's called the scientific method, and that's the subject of the second half of this lecture. The scientific method is an amazingly complex, variable human process. It differs in detail from scientist to scientist, from discovery to discovery, but the method can be idealized as a four-step cycle of observation, synthesis, hypothesis, and prediction, as you can see on this diagram. The first step in most scientific studies is the collection of data. That includes observations, measurements, and perhaps experiments that you design. And these data can be tabulated into monographic studies of objects. They can be completed. You can collect them in various ways. For example, I showed you the bird book earlier. In a bird book, if you look at it carefully, there's an incredible amount of detail. They have pictures of the male and female species, but they also have information on the habitat, on the various migration routes, even the song patterns of various birds. All that will be collected in one of these monographic treatments. In mineral books, the same sort of thing. Mineral descriptions are just amazing. You'll have pictures of all the different kinds of crystal structures. You'll have tabulations of angles between crystal faces, chemical composition, physical properties, all sorts of tables and charts that give you information. Many approaches to compilation of data involve tables, thick books of tables. So you can, for example, see a table like this one, which is a chart of thermal expansion coefficients of solids. You see page after page, sometimes hundreds of pages, each with dozens of lines giving you various information about these properties. You'll notice in this particular table that one of the columns is marked REF, R-E-F. That's the original reference where the different measurements are reported. So this book is a compilation of literally hundreds and hundreds of separate scientific papers that give that information. At the end of every table, you're going to find that long list of reference, so you can go back to the original source. And then if we look at the scientific method, you'll see the next step, the second step. In this idealized method, the second step is the recognition of patterns. It's really a search for symmetries. See, most scientists have a deeply held belief that there are regularities and patterns in the physical universe. This recognition of a subtle pattern from amidst vast amounts of data, often after many years of intense study, that's one of the most creative aspects of science. It's the art of science, if you will. Sometimes this step involves recognizing similarities among what seem to be at first different phenomena. For example, the British physicist Michael Faraday discovered that several widely different phenomena, including the shock of an electric eel and lightning and static sparks on a cold, dry day, are all just forms of one phenomenon, electricity. So it's unifying, seeing that pattern in nature. Sometimes the steps of mathematical synthesis, fitting disparate data into one type of equation. And we're going to see that when we talk about Johannes Kepler and his discovery of elliptical orbits of planets. As also Isaac Newton when he discovered that one kind of gravity affects both objects on Earth and in the heavens. Now, once a pattern is found, the scientist is going to propose a possible explanation in the form of a hypothesis, and that's the next step in this scientific method. forming a hypothesis. Often this step is as straightforward as generalizing the synthesis step. All types of electricity are manifestations of the same phenomenon. That's what Faraday would have said. All planetary orbits are elliptical. There's Kepler. All objects in the universe experience the same gravitational force. That was Newton. And once the hypothesis is well tested, it might actually assume a higher status. If it's mathematical in character, we call it a natural law, like Kepler's laws of planetary orbits, or Newton's universal law of gravitation. And these laws are expressed usually as equations. And then alternatively, if a hypothesis is of a more descriptive nature, then it can be elevated to the status of a theory, such as Darwin's theory of evolution by natural selection. I want you to note carefully that when scientists use the formal word theory, they're speaking of a rigorously tested concept. This doesn't mean some speculation or random guess. You know, creationists sometimes attack Darwin's ideas on evolution as being only a theory, implying that it's on shaky ground. As we see in lecture 57, that's just not true. Okay, then we come to the fourth step. The fourth step, if you have a hypothesis, a theory, a natural law, it has to lead to predictions. A scientific hypothesis has to be testable. So Kepler's laws, for example, predict a pattern that should be followed by all objects ordering the sun. You can test the prediction by studying orbits of newly discovered comets or asteroids. But wait, see, this situation leads to a disturbing fact. You can't ever completely prove a scientific theory or a law. That's an amazing comment. Think about it. A scientific theory can never be completely verified. However, it's always possible that a scientific theory might be disproved by an unfulfilled prediction. So science is vulnerable to attack for exactly this reason. A single odd fact has the potential to undermine a long-standing theory. See, each counterexample has to be laboriously scrutinized, and this is why supporters of the theory of evolution often find themselves very much on the defensive when they engage in public debates with creationists, because creationists love to throw out odd assertions that seem to invalidate Darwin's theory. A single fact that keeps popping up is the report of human footprints in ancient sediment from age of the dinosaurs and even earlier. So according to the theory of evolution, you see, humans didn't appear on Earth until long after the last dinosaur became extinct. So if indeed there were a fossil footprint found in rocks hundreds of millions of years old, it would call into question many of the precepts of evolution. So each such anomaly needs to be examined carefully with time-consuming techniques to sort out the mistakes and the forgeries and so forth. Well, there's one more step. I've described this idealized scientific method as a kind of cycle with observations, synthesis, and hypothesis and so forth. But there's one more aspect that's critical. You'll see at the center of this idealized cycle that there's always a paradigm. That's a prevailing system of expectations about the natural world. Those expectations guide what scientists ask about what they decide to study, what they choose to question in their laboratories. You know, we wouldn't ask questions about life on other worlds if we thought that life on Earth was a unique phenomenon. And there are many important and interesting scientific questions probably remaining unasked because they lie outside any current paradigm. And this is one of the really important reasons why I think science should eagerly recruit women and men from many, many different backgrounds. You see, different people bring different perspectives to science. I think the vibrancy of the scientific enterprise can only be judged by the richness of the questions they were asking. And that richness directly reflects the diversity of people who are asking the questions. Now, I should tell you right up front that the scientific method is rarely followed as this exact cycle I've shown you. Human imagination plays a role, intuition, chance, they're vital elements of the dynamic scientific process. And we're going to explore some of those variables in the very next lecture. But first, let's look at an historical example that's often cited as the epitome of the scientific method in action. And that's Dmitri Mendeleev's development of the periodic table of the elements. Here's that periodic table. It's so familiar. You've seen this table that systematizes every known chemical element. It adorns thousands of science classrooms and laboratories around the world. You'll find it in almost every science textbook. It's just so important and fundamental to modern science. When Mendeleev developed this table in the mid-19th century, he had gathered data on 63 different elements. That's enough to begin to see some patterns. You know, he expected to find order in this collection, and so he started to group them according to their similarities. He ordered the known elements left to right according to their weight. He also grouped them by their distinctive chemical and physical properties, and he aligned them in vertical columns according to those properties. The table that resulted, it turned out, had gaps. For example, Element 21 was missing. What we now know as scandium was unknown in Mendeleev's time. So Mendeleev's table led directly to the prediction of the weights and the properties of that and other new elements. This story about Dmitri Mendeleev is compelling, but science doesn't always work in quite such a linear fashion. In fact, it's often the anomalies, the things you don't expect, that lead to new insights. There's a historian of science, Evelyn Fox Keller, who wrote about this. Let me read you a quote from Evelyn Fox Keller. She says that when scientists set out to understand a new principle of order, one of the first things they do is look for events that disturb that order. Almost invariably, it is the exceptions. It's in the exceptions that they discover the rule. It's in the exceptions that they discover the rule. When anomalies are found that violate well-tested theories and laws, it usually means that the old theory or law is a valid special case of a more general law. And let me show you an everyday example. That's the hypothesis that objects fall under the force of gravity. And I can demonstrate this because I can take an object and I can drop it. And it falls. I can take other objects and I can drop them. And each object that I take, I let it go and it falls. And you can do this. Now, your hypothesis that objects drop when you let go of them can be tested quite simply. You just drop more objects. And you can keep doing this over and over again. You can drop 1 million objects and it will seem to be true. And so you form this hypothesis. And you've made a prediction. The prediction is that when you drop objects, they're going to fall. But you have to be able to test and falsify your hypothesis. And then you go drop one more object. You drop a balloon like this, and oops, suddenly something different happens. In fact, the balloon falls up. This anomaly of a helium-filled balloon leads to deeper understanding. In the case of the balloon, it turns out it's less dense than the surrounding air, so it's the air that falls, causing the balloon to rise. The same sort of situation occurred as a result of careful study of Isaac Newton's great laws of motion. We're going to examine those in Lecture 5. What we'll find is that all Newton has experienced was with objects that moved rather slowly compared to the speed of light. And so his laws cover only those everyday events that we experience. Early in this century, Albert Einstein showed that Newton's laws fail for objects traveling near light speed. Yet this discovery didn't invalidate Newton. It just turns out that Newton's laws are a special case of Einstein's more sweeping theory of relativity. Geneticist Barbara McClintock underscored this point in her Nobel Prize-winning work on corn genetics. Other workers at the time believed that a simple relationship existed between individual genes passed down from parents to offspring, and those are the genes that determine the characteristic of individual corn kernels. What McClintock said is see that one kernel that was different and make that one understandable. And in the process, she discovered the remarkable fact that genes occasionally jump. They move, providing an additional and previously unexpected mode of genetic variation. So you see, the scientific method is not a strict guidebook. Rather, it's sort of an idealized path to knowledge. It often seems to fit better in retrospect than while we're actually making the discoveries. Well, to summarize this lecture, first I considered 6 different aspects of scientific questions. First was that many important questions are beyond the realm of science. Science can't answer if there's a God or tell you the meaning of life. Scientific questions are also richly varied in scope and content. We saw that we have existence questions, origin questions, process questions, and applied questions. And then we said answers to old questions often lead to brand new questions, because the more we know, the more we realize how much we really don't know. And then scientific questions are often interconnected in surprising ways by their content or by their philosophical approach. A fifth aspect was that some questions, like the mechanisms of consciousness, are not now scientific, but may be someday as our understanding grows. And finally, most questions can't be answered completely. Then we looked at the idealized 4-step scientific method, which includes observations, experiments, collecting data first, then recognition of a pattern in those data. That's followed by development of a hypothesis or a theory. And finally, predictions. But those predictions always lead to more observations, and so the cycle goes round and round. The scientific method is an elegant process for learning about the natural world, but it's neither intuitive nor is it obvious. In the next lecture, I'll chronicle the gradual emergence of the scientific method during the past 5,000 years.